Click. All right. So, the original plan for the end of this week was on Wednesday we'll hit some things about proving new identities for mold. Then Thursday was going to be a second day on that. I'm making a change. That Thursday is, I think, just going to be another review day for the midterm/final. So there will be 2 review days in a row. On either Wednesday or Thursday, I'll hand out the course evals for people to fill out. So if the next 2 days you bring a number 2 pencil to class, I'd appreciate it. I'll have some of my own, but not enough for everyone. And then after that, it's final exam and stuff. I haven't posted a review for the final yet. I will soon, ideally today. How many people feel impatient like they'd like to see a review for the final immediately? All right, let me show you how to get one. So here's the course webpage. If you go to the URL and just X out that much, you'll get to my personal webpage. This has all of the classes I've taught previously. Go to the last time I taught pre-calc. There's a sample for that final. The thing that I'll post will be super similar to this. The final doesn't change that much semester to semester anyway. There's a review you can see. It might not be the same as the one in my handout, but it'll be damn close. How many people think they might actually do that? All right, cool. The other thing that maybe is worth saying is on the Friday of next week, I think I'm going to have a review activity for the final, and that'll be counted for some very small amount of points mitigation on the final. So, on the one hand, if you're not feeling totally confident on the final, you should probably come to all the review days anyway. But like, the review, I'll like cap the things it can help you with at like 75 or 80%. But if you're concerned you might do badly on the final, get yourself some wiggle room. Avoid at least some stress that way. Neato. So, let's start in on the content for today. Unless people have any other logistics questions. How many people have already looked at the review for the midterm that I posted online? Okay. There's a review for the midterm posted online. I'll hand it out next time, I think. Right. And this is what I want. So, let's state some more trig identities. So, what do we have so far? We have angle addition formula for cosine and sine. And maybe it's even worth putting those on the board. Remind me what those say. So the angle addition formula for cosine says cosine of A plus B equals what? Yeah.
Cosine A times cosine B minus sine A times sine B.
How many people are planning on having that formula on their note sheet and stuff? Nice, yeah, we were sure. Even if you think you have it just built into your brain, it's worth it. What about the sine of A plus B? Anyway, in like the wall, if you're out and you need to use an angle addition formula, it's much more important to know that they exist than to internalize exactly what they say. Because if you know that they exist and roughly when they apply, you can look them up when you need them. Here's the last formula I'll try to get out of this packet. Tangent A plus B. And on the one hand, there's space for derivation there. But I think in order to just stay on schedule, let's just write down the formula. The tangent of A plus B is equal to tangent A plus tangent B. And then I'm going to divide by something. So as is, that looks like a really nice formula. It just says if you add together 2 angles, you add together their tangents. That can't possibly be right, though. There's like not many functions that do that. The only functions that do that are multiplication by a constant. So it's that divided by 1 minus tangent A tangent. And especially since I haven't written down the derivation, let's see that it's correct by looking at a Desmos graph. So what will I do? Let's pull up a graph. I want a new graph. I'll build this little slider called A. And I'll graph tangent A plus x. That looks like what it should look like, right? It's just shifted over by A. Let's also graph tangent of A plus tangent of x divided by 1 minus tangent of A tangent of x. Seems to line up pretty good? Cool. And maybe it's an accident that A is 2, so let's try different choices of A. They seem to line up okay? Nice. So we have angle addition for tangent. I'm going to put that here also. Tangent of A plus B is tangent A plus tangent B divided by 1 minus tangent A tangent B. And what if I go and change this B to negative B? Maybe I'll go up here and do it. So, what do you think should change if I replace that plus B with a minus B? Well, subtraction is addition, right? It's just adding a negative. So if I want to make that B a minus, then those two B's will just become a minus B. People feel okay right now? Is tangent even or odd? One eye on. I hear a call for odd. Let's just see how people feel. Even? Odd? If I don't remember, I would like to see a fast and quick way to call on a spot. Let's remember what tangent means. Tangent is the slope of a line. Insert at the origin and rotate up by an angle theta. Tangent is the slope. So let's rotate up and rotate down. Do those two have exactly the opposite slope? Nice. So that's how to remember. So to get the subtraction formula, I just need to take this formula and replace tangent of B with negative tangent of B. So this will become 1 minus, nope. It'll be tangent of A minus tangent of B all over 1, and then it'll be minus tangent A times negative tangent B. There's a double negative there, that'll become a positive. 1 plus tangent A tangent. Tangent of A plus B is tangent A plus tangent B divided by 1 minus tangent A. Cool. So, just in order to remind you why these formulas are useful, let's use these to compute something that we couldn't before. Let's compute tangent of 7 pi over 12. So, how many people remember how we computed like cosine of 5 pi over 12 last time? How many people at least remember that we did it? So let's flash back to the notes and see like what the ideal was. Cutting whatever. So I'll flip back here. So what was like the idea we used to compute cosine of 5 pi over 12? Yeah.
You use things on the unit circle with values you knew, and then use the formula to figure it out from there.
Nice. So we're going to use the same strategy. We need to find some things on the unit circle that add up to 7 pi over 12, because that's what I want to compute. And then I need to use this formula. So look at your unit circle. You see two angles on it that seem likely to add up to 7 pi over 12. Or subtract to 7 pi over 12. feel like they have no idea how to proceed. Let's just try some shit. Now give me an angle on the unit circle. I'm not hoping that it works out correctly, just give me an angle on the unit circle.
Sorry.
Which one?
3 pi over 4.
3 pi over 4. Give me another angle on the unit circle.
5 or 6.
Pi over 6. Should we add or subtract? Which would you like? All right, we'll add. Let's add those angles together and hope that the result is 7 pi over 12. Yeah. Yeah, sorry about that. So, to add these two, I need a common denominator. So let's get that common denominator. What's the common denominator between these two? 12. That's nice. I'd like to have 12 in the denominator. This will become, let's see, 9 pi over 12 plus 2 pi over 12. Does that add up to 7 pi over 12? Subtraction would do the trick, though. So let's replace that addition with subtraction. Does that now give us 7 pi over 12? Do we have an angle subtraction formula we can take advantage of? Sure do. So if we are to compute tangent of 7 pi over 12, well, we've just discovered that that's the same as tangent of 3 pi over 4 minus pi over 6. That seems promising so far. Let's use angle subtraction and see what happens. So this will be equal to the tangent of 3 pi over 4. I want to subtract, so I should subtract tangent of pi over 6 all over 1 plus tangent of A, so tangent 3 pi over 4, multiplied by tangent of pi over 6. And the reason we chose these angles is because we know what tangent is at those angles. Or at least we should. So let's write those down. Looking at unit circle, what's the tangent of 3 pi over 4? -1. What's the tangent of pi over 6? All over 1 plus tangent of 3 pi over 4? Multiplied by? All right, so we have ourselves an exact value right there. Is it a simplified exact value? Nope. What are some things I see? I see like there are fractions in the numerator and denominator. So I guess I should get a common denominator just in the numerator, add fractions. Get a common denominator just in the denominator, add fractions. Then multiply by the reciprocal maybe, and then well we'll just see where we go from there. So this sure looks like in the numerator I have, let's see, minus 3 minus the square root of 3 parentheses all over 3. That divided by 3 minus root 3 all over 3. Anyone have any questions about what happened in that step? That step seemed correct? During my earlier section, it became very clear that I'm incapable of doing anything correct today. So, did I do anything wrong yet? Cool. What should I do next? Yeah, if you divide the numerator and the denominator by 3, those just cancel. If you want, maybe you'd multiply by the reciprocal and then cancel. All right. So I see negative 3 minus root 3 over 3 minus root 3. Is that maximally simplified? I see a square root in the denominator still. So when you see a square root in the denominator, it's a decent practice to multiply and divide by the thing that rationalizes the denominator. So, what should I multiply and divide by? Not just root 3. It turns out the right thing to do in this situation is multiply and divide by what's called the algebraic conjugate. And it's called that because it looks like the complex conjugate. And we'll see why that's the right thing to do right now. So let's FOIL out the numerator and denominator and see what we get. So I think I see negative 3 times negative 3 is negative 9 minus 3 root 3 minus 3 root 3 minus 3 all over 3 times 3 is 9 plus 3 root 3 inside minus 3 root 3 last minus 3. Anything helpful about to happen? A lot of cancellations. And I guess here's the most important one. Is there a square root in the denominator anymore? Nice. So let's just write out what this becomes. Negative 9 minus 3 is minus 12. Minus 6 root 3 all over 9 minus 3 is 6. And I painted myself into a corner, so I don't have space to do another line. Is that a maximally simplified answer now? Any common denominators between that numerator and denominator? Yeah. I guess 6. So I'm going to do something that I get upset when you do it on the homework. I'm going to go all out of order. What I really should do is get a new clean piece of paper and rewrite this. Minus 12 divided by 6 is minus 2. 6 is canceled. Minus 2 minus root 3. Does that at least look simpler than what we had before? Nice. There's the tangent of 7 pi over 12. It's minus 2 minus the square root of 3. How do people feel about that computation? I go, okay. And, in fact, the main point is, if you could get there, I'm pretty happy. Yeah.
Is there any reason to suppose the 7 pi over 12 can just do addition?
Oh, yeah, let's do that too. How could you also write down 7 pi over 12? 3 pi over 12, also known as pi over 4, plus pi over 3. Yeah, there's more than one way to shake a stick. There are other ways you could also have written it down. This way works well.
I just don't know if this is
No, it's because it's the one that came up naturally in conversation. Neato. How many people, in fact, did it on their own as that addition beforehand? Okay, well, I guess I can't ask if you got the same answer then. Hopefully you would. Cool. Any questions before we move on? Nice. Then I'll go ahead and announce, as has been the theme in a lot of these, there's a lot of extra credit. If you want to see why angle addition is true, there are 2 separate arguments for angle addition in the next pages in the notes. Both of them just do a lot of geometry. If you prefer triangles, then do the triangle one. If you prefer unit circle, then do the unit circle one. It turns out that complex arithmetic has a lot to do with trigonometry. If you start drawing points in the complex plane as x1 plus y times the imaginary number, then it turns out multiplication to something really interesting. In this extra credit, you'll figure out what that interesting thing is, and it has to do with angle addition. But what I actually want to get in on today is half angles. So, I'm going to start by just recalling the double angle formulas. Cosine of A plus B is cosine A cosine B minus sine A sine B. Sine A plus B is sine A cosine B plus cosine A sine B. Tangent A plus B is tangent A plus tangent B. Well, I don't have enough space. Divided by 1 minus tangent A tangent. So those are just the same formulas as are on the board. This is worth having them written down multiple places in the notes. So one thing we did last time is we made the observation that if you know how to add angles together, then you can figure out how to multiply an angle by 2. Because what does it mean to multiply a number by 2? Add that number to itself. So 2 theta is theta plus theta. And while we did get formulas last time, let's rederive at least one of them on the spot. More if you want. So there's space over here. There's enough space. So if you want to compute sine of 2 theta, that's the same thing as sine of theta plus theta. And maybe before I go on with the derivation, how many people just remember the double angle formula for sine? What is it? Oh, cool. Let's write it down then. So, sine of theta plus theta. Well, I know what happens when you add angles together. You can use this formula. And it looks like just A and B are both theta. So this is the same thing as sine theta cosine theta plus cosine theta sine theta. Does anything simplify there? What does that equal to, really? Does it matter what order you multiply numbers together in? So it's really a single product added to itself. So what is that?
Cosine squared theta, sine squared theta.
Not quite. It's this number plus itself. So it's just that thing multiplied by 2.
Oh.
So sine of 2 theta is 2 sine theta cosine theta. And cosine 2 theta, they're really like 3 different identities that I'll write down. Different ones are useful for different things. So first we'll get the one that's the most obvious to, let's try to do this without actually writing down a whole lot. So I want to use this formula, cosine A cosine B minus sine A sine B, but with A and B both equal to theta. So to get cosine of 2 theta, it'll be cosine theta, also known as cosine squared theta. Yep. Cosine squared theta minus sine theta, also known as, there's one of the double angle formulas for cosine. Oh, but that has a cosine squared and a sine squared in it. A lot of what we've done has involved the idea that if you see a cosine squared and a sine squared, you could just see a cosine squared, right? And if you did that, maybe I'll write down the thing and then we'll see if people want to go through the derivation. This is the same thing as 2 cosine squared theta minus 1. Should we go through how to go from the line above to the thing I just wrote? Nice. Let's do it. So, off to this side, what do we have right now? Cosine 2 theta is cosine squared theta minus sine squared theta. I'd like to get rid of this sine squared. What's like the important fact that relates sine and cosine? One is x and one is y. That's true. The thing I'm fishing for is the Pythagorean identity. What does it say? when you add together cosine squared and sine squared, you always get 1. Cosine squared theta plus sine squared theta is equal to 1. Could you solve that for sine squared? What would you get? Cool. Let's use that. So cosine of 2 theta is apparently also equal to cosine squared theta minus 1 minus cosine squared theta. All right. If you distribute the negative sign and combine like tongs, what do you get? If you have to actually distribute the minus sign on paper, then do it. 2 cosine squared theta minus 1 is what I hear. Is that what I wrote down, I hope? Could we have equally well instead gotten rid of cosine squared instead of sine squared? Yeah. And it would be the same walk. What you would wind up with is 1 minus 2 cosine squared theta. We won't go through the walk this time. Folks feel pretty all right? Tangent. We know how to add tangents together. Let's use this and see what happens if we plug in a equals b equals theta. So I guess it'll be tangent theta plus tangent theta in the numerator. So that's 2 tangent theta. 2 tangent theta divided by 1 minus tangent theta tangent theta. Cool. Folks feel okay about that? All right. So, double angle formula is useful in that it allows you to do computations you couldn't before. Let's use this to do a computation that we couldn't before. So let's suppose I give you an angle. Let's suppose I tell you that the sine of that angle is 3/5, and pi over 2 is less than theta is less than pi. Then let's compute cosine 2 theta, sine 2 theta, and tangent 2 theta. And I know things are written down in some order on this page, but let's motivate it by starting just down here at the double angles we'd like to compute. What's the formula for, well, we have 3 formulas for the cosine of 2 theta. And right now I know what the sine of theta is. So which of those 3 formulas looks most useful right now? You want the first one? We could use the first one. So that would write down that this is equal to cosine squared theta minus sine squared theta. Do I already know cosine squared? I don't. I already know sine squared. Maybe you already know cosine. So you know sine, you need to know cosine. That's okay. We can figure it out. What's the formula for the sine of 2 theta? Do I already know sine theta?
Yeah.
Do I already know cosine theta? No. And the double angle formula for tangent is 2 tangent theta all over 1 minus tangent squared theta. And I don't know what tangent of theta is. Well, let's do this. So I know sine of theta is 3/5. If you know sine, how do you find cosine? There are 2 good answers, both of which are kind of the same. Pythagorean identity. Or we could draw a right triangle. Let's use the Pythagorean identity. So the Pythagorean identity, Gesundheit, says that cosine squared theta plus sine squared theta is equal to 1. Don't know what cosine is, so I'll replace it with a c. C squared plus 3 over 5 squared equals 1. That look like something you could solve for c? Hope so. What do you get? Or should I actually do the algebra? Want me to do the algebra? All right, I do algebra. What's 3/5 squared? What's 3 squared? 5 squared is 25. I'll rewrite that one as a 25 over 25 because I'm about to have to rewrite it as 25 over 25 anyway to do subtraction. So subtract 9 over 25 to the other side. C squared equals, let's see, that'll be 25 minus 9 all over 25. What's that numerator equal to? 16. So C squared is 16 over 25, so what is C? Almost. It's plus or minus 4/5. Is it plus or is it minus? I call it minus. Why minus? This thing that I did not emphasize until now says that this angle is in quadrant 2. So cosine is negative 4 over 5. Is that now enough information to do the next two items? Cool. Let's do them. So I guess these computations are things that you can just do now, right? Do I know what cosine is right now? It is negative 4 over 5 squared minus, do I know what sine is already? 3 over 5. Then it gets squared. Oh, cool. That looks like something that one could compute. Sorry, I'm stalling because I don't want to do it. Yeah. I hear 7 over 25. Do I hear a second for 7 over 25? Do I hear a counterpart to 7 over 25? I think 7 over 25 is right. And that's what I seem to remember getting. What about sine of 2 theta? Do I know sine theta? I know cosine theta now. So it looks like I just need to do some multiplication. And by I need to, I mean you. Cool, yeah. I've got a negative 4/5. Do I hear a second? Do I hear a disagreement? I should hear a disagreement, but I think that's all right. Say that.
No, I said it's fine. Oh, okay.
Let's go do it. So it will be 2 times. Do I know what sine of theta is? 3/5 times cosine of theta is negative 4/5. And let's work out what this is. Yeah.
Negative
0.96. Did you do that by just asking a calculator that whole thing? Oh, okay. What fraction did you get? Yeah.
Oh,
Negative 24 over 25. Oh, yeah, did you say positive or negative 0.96? Okay, that's good. I lost the negative sign. Nice. Did you catch anything that went wrong when you said forehands? Excellent. Cool. So, there's cosine 2 theta, there's sine 2 theta. So on the one hand, we have this double angle formula for tangent. But if we already know sine and cosine, can we figure out tangent? Yeah, so let's do both. So tangent is the same as sine over cosine. So that'll be negative 24 over 25 divided by 7 over 25. What simplifies there? If you divide the numerator and denominator by 25, that doesn't actually change the result. Right, like 4 over 6 is the same as 2 over 3. Equals negative 24 over 7. Well, let's also do it using the double angle formula. Do we already know tangent of theta? Well, maybe that depends on who I'm asking. How many people have already computed tangent of theta? Do we have enough information that it's easy to compute? Yeah. Are you on negative 34? Do people? That seems right, because it should be sine over cosine. All right, let's use that. So this should be the same thing as 2 times negative 3 over 4 divided by 1 minus 3 over 4 squared. All right, there's another slightly annoying bit of arithmetic to do. And I guess I know what the answer should be. It should be negative 24 over 7. So I guess one of two options. Get a decimal approximation for that, or simplify it. Either way, tell me what you get. Does it simplify that to 24 over 7 with a negative sign? Nice. I don't want to be the one to do like the fraction reduction, but it is useful to be able to do that stuff. So I guess it should be negative 3 point some change if you got a decimal approximation. That agree? Groovy. So, take away, so here's a common exercise that I'll have you do to use the double angle identity. I'll give you something about a trig function. I'll ask you for something about a double angle of some trig function. To do that, it looks like you need to compute sine and cosine, maybe. If you just want a tangent of 2 theta, you wouldn't need to compute those two. And then use the right formula. Cool. So the last formula I want to get today. And the thing that I kind of wanted to start with today, according to the schedule in the notes, so I think I'm going to make some more revisions to the schedule once I get back up to my office. Is let's figure out what cosine of half an angle is. And it seems philosophically reasonable that we should be able to get a half angle. Because I have a double angle formula. So if I like just do the opposite of the double angle formula, I should get a half angle formula. It's like philosophically it seems reasonable to get. Let's go through the wall. And here's the way I'll put rubber to the road and do it. So I'm going to put this in a blue box for now. So certainly cosine of theta is the cosine of 2 times theta over 2. That's true, right? Multiply by 2 undoes divide by 2. Here's why I'm doing it. I'd like to get a theta over 2 in play. And I know what happens when I multiply a thing by 2. So this will accomplish those goals. And now let's use a double angle formula for cosine to do this. And in fact, I think I'll use this double angle formula for cosine to do it. So let's use it. So I have cosine of 2 times box. The formula that I just circled in orange says that this should be the same thing as 2 times cosine squared of box minus 1. What goes in that box? Just theta over 1. The 2 times is built into the fact that I'm double angle formulating. The thing in the box is just theta over 2. And that's helpful because I would like to know what the cosine of theta over 2 is. So let's just underline all of this. Oops. Okay, no, my screen just died, but that's okay. So cosine of theta is equal to 2 times the cosine squared of theta over 2 minus 1. Does that look like something you could solve for the cosine of theta over 2? I think so. So let's do it. I want to get this on its own. So what should I do to both sides to get that on its own? Add 1. And let's do the next step too. Add 1 and then divide by 2. So if you add 1 and divide by 2, you will get cosine theta plus 1 all over 2 is equal to cosine squared theta over 2. All right. Well, what if you want the cosine of theta over 2? What do you still want to do to both sides? Square root. Let's see what happens if you do that. Any objections right now? There's a plus or minus issue. So I'm going to stick a plus or minus in red there. That's kind of weird that there would be one, but I think there has to be because of the following. So let's graph both sides of this. So this is where this QR code goes. Unfortunately, this thing doesn't know how to do QR codes, so in red, I see cosine theta. The dots are this formula for what this thing is. Do they line up exactly on the nose? Is the dotted one the same as the solid one, at least up to a plus or minus sign? Yeah, so the cosine of theta over 2 is, in fact, plus or minus the square root of cosine theta plus 1 all over 2. And there are formulas for tangent and sine as well. Sine of theta over 2 is plus or minus the square root of 1 minus cosine theta all over 2. So the half angle formula for sine involves cosine, which is kind of weird, but sometimes things are weird. And there's also one for tangent. And let's write that down, and then I think that I'll be about out of time. Tangent of theta over 2 is, well, let's compare the thing for sine first. Do those two also look like they agree up to a plus or minus? There's tangent of theta over 2. Do those two look like they just agree? Nice. So tangent of theta over 2 is 1 minus cosine theta all over sine theta. Nice. I think that's where I'll stop. I have like minutes left, but that's not enough time to actually do an example. So we'll continue in on this next time. Cool. Anyone planning on coming up to my office hour? Oh, I should say this. If you don't have your midterm 2 exam back yet, I have it. It's in my office. You just won't hear on the day that I hand it back. If you'd like it, just come see me today.